We're going to talk about how to jam nonlinear specifications into a linear regression, and we call that a nonlinear regression. We do that because, as you've probably noticed, economists are good at wringing every last drop of juice out of any good idea. Good ideas are rare. We got to squeeze it for all they're worth. Linear regressions, OLS, are one of those rare good ideas, and we want to get a lot of use out of it. Nonlinear models are generally how the world works, and a linear model is often a simplification or admission that, well, we don't actually know that much. It's a first-order guess. If you remember the Taylor series from calculus, any differentiable function can be approximated within a neighborhood by a linear function. Now, not every function in the world is going to be differentiable. Certainly in your finance classes, you learn about variables with non-differentiable paths. But for a variety of cases, we're comfortable specifying the relationship should be smooth. The higher order polynomials sort of spill right out from the Taylor series idea. How do we use a linear regression with a nonlinear term? Ordinarily, a multivariate regression sets y equal to beta naught plus beta 1 x1 plus beta 2 x2, etc. But what if for x2, just move that 2 up and call it x squared instead? Or for that matter, any other nonlinear function of x like log x. The answer, it works fine. It goes right on through. Let's do an example. I regress wage on beta naught plus beta 1 age plus beta 2 age squared plus some other stuff plus my error term. Remember your calculus class. How do I find the derivative of y? Or in this case, the derivative of wage as age increases. Take the derivative with respect to age. That's going to be beta 1 plus beta 2 times age. That's the first derivative of that parabola. Often we estimate that beta 1 is positive and beta 2 is negative. That shows that people's age increases their wage at first, but then gradually the wage increase on your birthday gets smaller and smaller till eventually you're over the hill. You stop getting a raise for your birthday and actually start declining. We can find that peak by setting the derivative equal to 0, since that's the local maximum. For different values of beta 1 or beta 2, it could be a minimum. If you like that possibility, you can add in higher order polynomials, x cubed, x fourth, etc. There are debates about how many higher order terms do you really want. There's a limit to their use. People debate whether to stop at x cubed or use the fourth power. You can test it. You can do a joint test for whether all the coefficients on these higher order polynomial terms are jointly equal to 0. We just talked about that. Note, we would not do tests of each term one by one, maybe drop the squared term but leave the cube. That's kind of weird to think you'd have such precise knowledge about one of those polynomial terms and not any of the others. It's probably just an error of the testing procedure. Just as we put in squared or cubed or higher polynomial terms, we can put in logs. We're not in elementary school, so log here means natural log, i.e. base e, because that's what makes sense. You could take the log of x, you could take the log of y, you could do both. Just remember Jensen's inequality. The mean of the log of y is not the same as the log of the mean of y. Yeah, you remember that. One of the reasons we economists often use logs is because, again from calculus, logs have an easy interpretation. In a regression, I have log y on the left. Each beta is interpreted as the derivative with respect to that x variable. And the derivative of a log is the percent change. If I have log x instead of x on the right-hand side, then I can interpret that coefficient as the change in y from a 1% change in x. And if I have log y and log x, then the coefficient is the elasticity.